Hello everyone, today is Pi Day and I thought I'd talk a little bit about something related to pi, but also about something that we are talking about in class right now, namely that of Fourier series and Parseval's identity. There's a nice problem in mathematics called the Basel problem, and I'm going to work out a solution to this problem using Fourier series and Parseval's identity. This problem was first posed in 1644 by Pietro Mengoli, and take a minute, pause this video and read a description about the history of this problem, which I incidentally took from Wikipedia. The problem essentially asks to find the exact value of the infinite series summation 1 over k squared. Summed from k going from 1 to infinity, which is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, so on and so forth. And Euler solved this problem in 1734 and remarkably showed that the exact value of this expression is, believe it or not, pi squared over 6. And we're going to show how to get pi squared over 6 as the solution to this sum of infinite terms in this series. And we're going to use Fourier series to show this. So let me quickly recall, we've been talking about the continuous time Fourier series, which says if I have a continuous time signal x of t that's periodic with a fundamental time period of capital T, then x of t can be written as summation x of k times e to the j k omega naught t, where omega naught is 2 pi over capital T. And we can find the Fourier series coefficients x of k's using the formula x of k is 1 over t times integral over one time period of x of t times e to the negative j k omega naught t dt. And of course when k is 0, this reduces to x of 0 being 1 over t times the integral over one time period x of t dt. And we also talked about a very nice relationship called Parseval's identity. And Parseval's identity essentially told us that if you try to compute the energy of, or rather the power of the signal x of t, you could either compute that in time as 1 over t integral over one time period of the magnitude of x of t squared dt, but this is also equal to the sum of all the Fourier series, the square of the magnitudes of all the Fourier series coefficients, summation going, k going from negative infinity to positive infinity. We're going to try to use these two expressions or results to try to solve the Basel problem. Okay. The idea is to do the following. The idea is to find a signal x of t whose Fourier series coefficients somehow look like 1 over k. So when I try to compute summation 1 over k squared, we would essentially be computing the power using the Fourier series coefficients, and if that signal turns out to be something such that the integral over one time period of x of t squared dt is easy to compute, then we could find an expression for the infinite series. Okay, so here is such a signal. So let's start with a periodic signal like this. So the signal is given by t when t is between negative pi and positive pi, and it's periodic. It's periodic with a period of 2 pi. So it keeps on going like this. So let's call this signal as x of t. And you will see that x of t is periodic with a fundamental time period of 2 pi, which also means that its fundamental frequency is 2 pi over 2 pi, which is 1. So what we're going to do is to compute the Fourier series coefficients of this signal and see if we can use Parseval's identity to then get the result that we want. All right, so how do we compute the Fourier series coefficients? Well, we just plug x of t into the formula and evaluate this expression. So one fundamental time period of the signal goes from negative pi to positive, rather one time period of the signal goes from, or one period of the signal goes from negative pi to positive pi. The signal is given by t. So the Fourier series coefficients can be computed as t times e to the negative j k omega naught times t, but omega naught is 1. I'll write it as omega naught times t, and then we'll substitute omega naught is equal to 1. So we just simply get k times t dt. This integral can be computed easily, except that you'll need to use method of partial fractions. I'm going to give you a minute, pause the video and see if you can compute this integral and get the following result. You should see that this integral turns out to be t times e to the negative j k times t divided by negative j times k plus e to the negative j k times t divided by k squared, and the limits are negative pi to positive pi. Oops, I'm sorry, I don't know what happened here. I'd suggest you pause the video for a minute and try to work this integral here. But if you're just interested in learning about the Basel problem, you can believe my computation is correct. Now if we try to plug in the limits here, let's try to do this for each one of these two terms. You get 1 over 2 pi, and if I try to plug in the limits for the first term, notice that I get pi times e to the negative j k pi minus negative pi times e to the negative j positive j k pi divided by negative j k. So that's what I get for the first term. And for the second term, I'm going to get e to the negative j k pi minus e to the positive j k pi divided by k squared. So this comes from this term. Now notice that the second term is actually 0 because e to the negative j k pi is the same as e to the j k pi. So this whole term goes to 0. And we're left with just the first term, which is 1 over 2 pi. And I can write this as pi times e to the negative j k pi plus e to the positive j k pi divided by negative j times k, which is 1 over 2 pi times pi times 2 cosine k pi divided by negative j times k. The 2 and the 2 cancels out, the pi and the pi cancels out, and the 1 over negative j can be written as j times, I get something nice, which is cosine k pi divided by k. And notice that cosine k pi is nothing but negative 1 to the k, and therefore the Fourier series coefficients are simply j times negative 1 to the k divided by k. Of course, for this to be true, k cannot be 0. If k is 0, we can go back into the expression, into this expression here, plug in k equal to 0, in which case you get integral of t between negative pi and positive pi. So x of 0 is 1 over 2 pi integral negative pi to positive pi t times dt, which is 0. So what this means is, if you look at the Fourier series coefficients, the term corresponding to k equal to 0 is 0. The term corresponding to k equal to 1 is j times negative 1 over k, and then I get j times 1 over, I'm sorry, it's j times negative 1 over 1. Then I get j times 1 over 2, j times negative 1 over 3, so on and so forth. And the same thing when k takes the value negative 1, negative 2, so on and so forth. Okay, now what's left is to try to apply Parseval's theorem. So let's try to compute. What does Parseval's theorem tell us? So Parseval's identity tells us that if I look at summation x of k squared, k going from negative infinity to positive infinity, that must be the same as 1 over 2 pi integral from negative pi to pi x of t squared dt for this particular signal whose fundamental time period is 2 pi. Now let's look at the left hand side here and notice what I get when I take the magnitude of x of k squared. The magnitude of x of k squared, when k is, let's start thinking when k is 0. When k is 0, the magnitude of x of k squared is 0. But when k is 1, it's 1 over 1 squared. When k is 2, it's 1 over 2 squared. When k is 3, it's 1 over 3 squared, so on and so forth. When k is negative 1, it's again 1 over 1 squared. When k is negative 2, it's 1 over 2 squared. So you can see that the left-hand side is 2 times summation k going from 1 to infinity of 1 over k squared. Does this look familiar? Well, it should, because this is exactly 2 times of what we are trying to compute. Just right here. I'll give you a minute to think about this. And now let's go back here. What is our x of t? Well, our x of t is equal to t. So this must be equal to 1 over 2 pi integral from negative pi to positive pi t squared dt, which is 1 over 2 pi t cubed over 3 between negative pi and positive pi, which when you substitute the limits, you get pi squared over 3, which tells you, dividing both sides by 2, which is indeed the solution to the Basel problem. Now, Euler's solution itself was not based on the Fourier series, and there are other ways to solve this, but I think it's particularly appropriate for what we were talking about in class, and given that it's Pi Day. So enjoy the rest of Pi Day. Bye.